And we'd like to welcome Natasha Jacques, who will be talking on social reinforcement learning.
Thank you so much. Thanks. I'm excited to be here. So I'm going to be talking about social reinforcement learning. I think most of us are familiar with reinforcement learning as a paradigm. So you have an agent taking a series of actions to maximize its long-term reward. And hopefully a lot of us are on board that deep reinforcement learning is pretty promising and has been showing some impressive results, especially in robotics. But we're also aware that it has a few issues. So some salient ones that come to mind are the computational complexity. If we look at AlphaGo 0, it needed to play 5 million games of Go to reach proficiency, which is about 560 years of human playtime. The other big issue is generalization, right? So the big joke is RL is the only machine learning area where you can train on the test set, right? We consistently see issues with RL algorithms generalizing to even slight modifications of their training environment, which of course is a huge problem if you want to do something like robotics where you have to operate in the real world. So the focus that my research asks is, what could social learning do for reinforcement learning? So what do I mean social learning? Basically, I mean a pretty broad definition, which just means learning from other intelligent agents that are in your environment. So this could happen through direct interaction and feedback from those agents, like if a human is providing feedback. It could happen when you're trying to cooperate or compete with agents, or it could also just happen when agents are coexist in your environment. So if you think about autonomous driving, there are lots of other cars on the road that might have valuable expertise that you could learn from, but you have to be careful about who and what you're learning from. So the reason I think social learning could be this really powerful mechanism is because we see all the time that it helps humans and animals do really valuable things, like generalize to new environments. So even this little 1-inch fish can locate safe sources of food in a dangerous new environment by looking at where the other fish are gathering and using that as a social cue. And in the UK, they have this nice example of birds learning to open milk top bottles, not because they each independently discovered this behavior, but because they were able to learn by observing other birds. And a lot of authors have argued that the key differentiator that sets humans apart from other animals is actually that we've taken these social learning abilities to the next level. And that's the driver of our intense, like, cognitive, cultural, and technological development. So I think social learning can provide a lot of these benefits to RL agents. So the first one is obvious. We know that individual exploration is incredibly expensive and time consuming. So you would never think about, starting with the technology of rubbing two sticks together and exploring randomly and hoping to discover the Large Hadron Collider. Like, that idea is almost laughable. And yet that's how we train our RL agents a lot of the time. Like, if we want to train this Mujoko cheetah to be able to walk, we have it randomly wiggle around until it discovers a policy about how to walk. But in contrast, social learning lets you stand on the shoulders of giants and learn by observing or building on what other people have already discovered. The other issue is that individual exploration can be really dangerous. So if you think about, let's say we were to train a robot that we want to operate in human environments, and we want to deploy it into a new neighborhood. If that robot randomly explores that neighborhood, it could put itself in a dangerous situation. So I actually managed to find an image on the internet of a robot getting hit with a car that I was very proud of. Kind of illustrates what could happen. But in contrast, if the robot could use social learning to look at where human pedestrians are walking, it can be more likely to be able to find safe places that it can explore. So I think this could be really powerful. Basically, I think social learning could help RL agents learn more complex behavior, adapt to new environments, coordinate with other agents, and ultimately improve human AI interaction. So this is what I'd like to convince you of today. When I say social learning, I do want to emphasize that I'm talking about both multi-agent interaction and human AI interaction. And I'm going to be focusing mainly on the first part today, but I'll briefly touch on the second part. So for today, I'm going to be talking first about coordination in multi-agent systems, and then about multi-agent training as a tool to actually improve single agent learning and generalization. So basically showing that multi-agent learning can go beyond coordination, can actually be useful for improving RL agents in general. And then I'll briefly touch on trying to learn from human AI interactions using similar techniques. So first, let's talk about the problem of trying to get multiple agents to coordinate with each other. So what do I actually mean by that? Well, a good example is thinking about trying to play robot soccer. We want multiple agents on the team to be able to coordinate their behavior to win the game, which might involve taking moves like passing the ball to each other. Now, there are a couple of issues with trying to do this. So if we think about how we could do this, one option would be, let's just learn a mega policy that decides the action for each soccer player on the field. So it's like some meta controller that controls everyone. The issue with this is that now your action space of the meta controller becomes exponentially larger in the number of agents you're trying to control. And this huge action space is really intractable. It's going to be difficult to collect enough data to learn this policy. So this is pretty hard. The other alternative would be to learn fully decentralized policies. So each agent is learning its own policy. The defender is just trying to learn how to do that. But the problem is that because all the agents are learning at the same time, they make the environment non-stationary. Like if I learn that your policy tends to put you over here at this time, so I'm going to pass to you, but then you update your policy, that's no longer valid, right? And the problem with the environment being non-stationary is that RL is the convergence guarantees of a lot of RL algorithms are based on a stationary environment. So you lose a lot of those guarantees. So that's a hard problem. So one approach that's been commonly taken in the literature is kind of the mix of two. It's called centralized training, decentralized execution, or CTDE. So I'll explain a bit more what I mean by that. A really canonical example of a CTDE algorithm is MADDPG. So the idea here is that we want at test time to be able to have fully decentralized policies that can operate independently. But we know that if we try to train in a fully decentralized way, that's really non-stationary and that's too hard. So what MADDPG does is says, let's have a centralized critic, basically a value estimate that we can use during training in the policy gradients training to be able to stabilize training, learn more effectively. But then at test time, we can remove the critic because it was only used for computing our gradient updates, and we can just operate in a fully decentralized way. So this paper has been massively popular. It's been built on a lot with many centralized critic methods. And one of the most popular of those is called QMix. So QMix basically had this insight that what we want from our decentralized policies is that if each agent learns its own value estimate and greedily takes the maximum of that when it's deciding how to act, we want the joint action chosen by each agent independently to be consistent with what we would get if we actually were able to estimate the joint value function and take the max over that. So that's the insight. The way that QMix enforces this, it says, okay, let's have each agent estimate its own value function, and let's combine those using this mixing network that enforces a monotonicity constraint. And so that gives us this nice property that we want. So QMix has been really successful. A lot of papers have built on QMix. But for my own work, I actually was very interested in this question of, could we train the agents in a fully decentralized way? And the reason I think that that's interesting is, if you think about real world problems of multi-agent coordination, I tend to think about something like autonomous driving, right? And so in that setting, you're not able to train with all the other cars on the road. The other cars are not sharing parameters with you or any privileged information. If you're the Tesla car, the Waymo car isn't going to send you information about its proprietary reward function. But what you can observe about those other cars is what actions they take in the environment. So I could observe if the Waymo car turns left, right? So what could we learn? How can we learn a coordinated policy in that setting? Now, we also had the intuition that maybe rewarding mutual information between agents' actions would create a bias towards learning coordinated behavior. So if you think about it, if two agents are coordinating, let's say two robots are coordinating to lift a heavy box or a piece of furniture. If one robot lifts the box faster, the other robot is going to have to as well to compensate, right? So they are exhibiting high mutual information between their actions when they are coordinating. So what we propose to do in this work was to give agents an intrinsic social motivation for having a causal influence on the actions of other agents. So what do I mean by that? How did that work? Well, first we took our normal deep RL agent and we augmented it with a series of sub-module basically that's predicting the next action that every other agent will take, conditioned on the action of the agent itself and the other agents. And we just train this with supervised learning on the trajectories that the agent observes. What that allows the agent to do is simulate counterfactual actions. So it can ask itself, what do I predict this other agent would do if I had taken this action instead? And using that, it can sample a bunch of counterfactual actions and sum over them to get the marginal policy of the other agent, or the marginal policy of agent B. This is basically what agent B would do if it weren't considering agent A. And the divergence between that marginal policy and the policy of B actually conditioned on A's action is a measure of the causal influence of A's action on B's action. And if you don't believe me that it's causal, you can check out this causal diagram on the right. You see that causality can't pass through an unconditioned on collider node like state at t+1. And so we know that there's only a causal path between action of agent A and action of agent B at t+1. But look, the causality stuff is kind of semantics. If you don't care about that, the punchline is that we are going to give this as a reward to agent A. Basically, agent A is going to get a reward if it takes an action that causes agent B to do something differently. Now, there's a pretty big problem with this. So I'm going to give you guys a second to think about what could be an issue with this, and I'm going to ask you to let me know after the end of the next slide. So think on what could go wrong here. I do want to point out that this is related to the mutual information. So if you look at the influence reward, you can see that it's this inner term of the mutual information between agent A's action, agent B's action. But the mutual information involves summing over the probability of the state and the probability of A's action. But of course, when we randomly sample many trajectories from the environment, we actually do bake in those probabilities. So we can show that in expectation, increasing the influence is going to increase the mutual information between agents' actions. And if you think about it, previous intrinsic motivations have often been in the category of empowerment, which asks an agent to increase the mutual information between its actions and its future state. You can think of this as a form of social empowerment. But okay, I'm going to pause here. So I dropped that question. Can anyone point out the very obvious issue with what could go wrong if agent A gets a reward for causing agent B to change its action?
Anybody in London fancy having a go at this? Yes, over there.
That it can eventually force the other agent to do something? Sorry. That it can eventually force the other agent to do something rather than observing its actions?
That's correct. Thank you, exactly. So, if I just stood in your way, I could force you to do something differently. You have to walk around me, but I haven't helped you. So how is this going to help us coordinate or play soccer or whatever? So we basically take two approaches to overcome this issue in this paper. And the first is to test in environments where cooperation is actually the hard problem. So what you're looking at here is a tragedy of the commons environment on the top, where agents are trying to eat these delicious apples. And if they eat the apples too quickly, they'll become depleted and not grow back. And so every agent greedily wants to eat more apples, but if they all do that, they'll all suffer. Similarly, in this cleanup environment, the agent has to clean the river in order to make apples appear. While it's busy doing that, other agents can exploit it or defect by eating the apples that it's farming. So we can prove that these are hard cooperation problems by looking at the shelling diagrams. So what you see here is the payoff you can expect to get if you follow a defecting or exploitive policy in red or a cooperative policy in blue, based on the number of other agents that are cooperating with you out of 5. So on the far right of the graphs, every agent is cooperating. On the far left, no one is cooperating. And what you can see is that as an individual, you can almost always get a higher payoff by sort of defecting on your little agent compatriots. But of course, if all the agents follow that strategy, then the payoff will be very low for everyone. And vanilla multi-agent RL algorithms have a lot of trouble finding this trade-off to be able to figure out that the cooperative strategy will give them a better payoff. And so what we see is that if we add this influence reward, the agents are actually able to cooperate more effectively as measured in terms of the total collective reward achieved, even though they're only individually maximizing their own rewards. So how is this possible? And I should mention that this actually exceeds the performance of prior work, which did have access to other agents' rewards. Let's look at how this works. So in this video, you see that the purple agent is the only one that's been trained with the influence reward. And the policy it's following looks a little different than the other agents. So when there are no apples, all the other agents continue to explore around to collect apples, but the purple agent stays still. And in fact, it actually only ever moves if there is an apple nearby. So how does that allow it to gain influence? Well, it turns out, let's look at a moment where it's able to influence this yellow agent. So the yellow agent can only see what's in that red box because the world is partially observed. So it can't see that delicious green apple that's outside of its field of view. But when the purple agent chooses to move towards that apple, which again, it only ever does if there is food present, it actually signals about the presence of food to the yellow agent, which changes the yellow agent's intended behavior and allows the purple agent to gain influence. And similarly here, you can see that the pink agent has been busy cleaning the river, but it can't see if any apples have appeared. When the purple agent chooses to stay still, that signals reliably that there are no apples, so the pink agent should keep cleaning the river. And what's interesting about that is basically now the purple agent has made it easier for the pink agent to follow a cooperative policy but still get rewards by signaling about this extra information that the pink agent didn't have. So essentially, this agent learned to use its actions to communicate about the presence of food in order to gain influence. So by giving information, it gained influence. And so what we thought, of course, is let's try to train an explicit communication protocol with this influence reward. So here we equip agents with a second policy that decides which of a set of discrete symbols to emit on a cheap talk channel. And we train that policy with the influence reward. So you get a reward if you say a symbol that causes another agent to change its intended action. Now, the agent's actions that they actually execute in the environment are only trained with the environment reward. So the only reason this self-interested agent should change its behavior as a result of a message is if that message helps it maximize its reward. So we think this is the second way of overcoming that difficulty that you identified earlier, which is that influence may not always benefit the other individual. In the case of cheap talk, we think that influential communication should benefit the listener. So let's see if that turns out to be true. I should mention that cheap talk between self-interested agents doesn't usually work. We know theoretically that as agents' interests diverge, the amount of information placed on the channel goes to zero. And we know empirically that this doesn't tend to work out. But when we add the influence reward, we can see that not only do the agents achieve higher collective returns, so they're managing to cooperate, they learn more meaningful communication protocols, so they're speaking about what they're doing or things that are in the environment. But this is my favorite slide, basically. What you see here is the degree of influence between agents on the y-axis and the agents being influenced on the x-axis. And you can see that agents that are more easily influenced or better listeners tend to get higher reward. And this is actually a very strong effect across hundreds of hyperparameter settings in both environments. So we see that being influenced tends to get you higher reward. We think that's because influential communication is providing you valuable information that lets you maximize your own reward. So I do want to raise a couple discussion points. Whether the action influence is pro-social is going to depend on the environment. So we think that in our environment, communicating information may be one of the cheapest ways to gain influence while still maximizing your own reward. Like, if you want to pick up apples, you can't just be getting in that person's way all the time. You actually have to go pick up apples. So this is, we think, why that arose. We think that influence on self-interested agents via cheap talk should benefit the listener, or should be pro-social, if you will. But of course, that depends on the agents interacting repeatedly. So if we had a communication protocol where I could communicate with a new agent that I might never see again, I could potentially lie to gain influence. All right, so in conclusion, I think of social influence as a unified method for promoting both coordination and communication in multi-agent settings. And it enables agents to learn socially, but train independently. So it doesn't require access to other agents' rewards or a centralized controller, as in previous work. Now, there's been a few follow-ups on this. This paper proposed 2 new methods for computing influence that work a little better. And this is a recent paper that benchmarked a bunch of state-of-the-art multi-agent algorithms in Google Research Football, which is the soccer environment. And you see that actually in this case, some of these influence methods are outperforming even QMix and Qplex. So that's kind of cool. But in all honesty, I couldn't recommend you use any of those methods because I've been playing around with Google Research Football and other multi-agent environments recently. And what I found works the best is actually just independent PPO. So basically separate independent copies of PPO agents. What you're seeing here is they absolutely crush those results in Google Research Football. Now this plot is actually unpublished. The only place I published this is to my email and this talk right now. And the reason I haven't published this result is because there's already several papers showing that independent PPO or even PPO with a centralized critic performs surprisingly well or amazingly well in a bunch of multi-agent benchmarks. So why is that? So it's actually the second paper that goes into this. Basically, they make the case through careful ablation studies that it's the stable updates in PPO that are based on inheriting like trust regions that make learning in PPO so stable that it's easier for other agents to learn with the other agents. So basically, I'm trying to learn to pass you in soccer. Are you going to be where I think you're going to be more likely to be yes because your learning is more stable? So I think that's really interesting. So I have to say, if I were recommending a multi-agent coordination algorithm today, I would actually say independent PPO. So I do want to, the next part of the talk is going to go into how multi-agent training actually goes beyond training agents to coordinate. But I want to pause here in case anyone has questions about multi-agent coordination in general.
Yeah, question over there.
Hey, Natasha. Thanks for that interesting result. So I'm actually a little confused about why trust region with independent PPO does well, because if I understand correctly, wouldn't the trust region apply to only the policy's current policy distribution? How would it know about the kind of updates that another policy is doing?
Right. It's basically saying the other policy that I'm learning against, it's updating more slowly and more smoothly. So when I'm trying to coordinate with it, I have a better idea about how to do that because it's not that its policy isn't jumping all over the place. So it's easier for us to discover and continue to benefit from coordinated actions, right? Essentially, it's just making the whole non-stationarity issue less severe. Like the environment is changing. If you think of other agents as the environment is changing more stably. Does that make sense?
Yep, thanks very much.
I have another question regarding the intrinsic motivation. So you mentioned this mutual information between your action and the action of the other agent given the current state. And you also mentioned empowerment. And people have been showing that empowerment, if you just compute the empowerment of the other agent, then you also perform cooperatively because you sort of help the other agent. So did you try this, or did anybody try this in this domain of deep reinforcement?
They have. So there's a couple of great papers by the first author is Guckelsberger. I could be saying that wrong, but they're really nice papers. And they focus on minimizing or maximizing the empowerment of another agent, which is quite interesting. The one paper I'm thinking of, he says, I think it's called New and Surprising Ways to Be Mean. And they're making a video game adversary that minimizes the empowerment of the player. And they actually end up with this like sadistic agent that wants to, throw the human player in like a lava pit, but won't actually let the human die. They'll pull the human out just before he dies and then push it back in to just continue to minimize the human's empowerment. So very interesting paper, definitely something you can do and is worth exploring. I prefer maybe assistance via empowerment is another paper by Yu Ching. I'm sorry, I'm forgetting her last name, but you could check it out. It's called AVE, Assistance via Empowerment. And the idea there is to increase the human's empowerment, to be a good assistant to the human.
There is also a question from the online audience. The question is, but if the independent PPO got another communication channel that is their enabled chip talk, it could get even better, right?
Well, presumably, you could guess that, but I actually, yeah. So this MAPPO paper here that I'm showing at the top, it does use a centralized critic, but instead of using like DDPG agents underneath or using a Q-learning based thing, just uses PPO. And it shows to be pretty effective. I wonder, I think there's a paper to be made that bakes off having MAPPO or having fully decentralized PPO. and just see what works better and maybe exploring that.
And there is a related question from a Panag at Google. Just to make sure I understand, is the lesson that PPO agents training independently with social influence and cheap talk is the best way?
Ooh, that'd be cool. That sounds fun. Let's write that paper.
Okay.
All right, I
So
do
you
want to
should
go
get in touch
into...
with the Panag at Google, so it should be a colleague of yours.
There you go, yeah. Yeah, I haven't tested that, so who knows. All right, so I do want to go on to the next part of the talk, because I think that's actually quite exciting. This is more cutting edge, I think. So I want to say that multi-agent training or social learning can actually go beyond just solving multi-agent problems like coordination. I think it can actually be this really useful tool for improving single agent learning and generalization. So this is a paper that I really liked. It's a thought piece paper, a position paper, and it goes through sort of the human psychology and cultural and sociology writing, and said that talks, there's another paper that I'm not citing here called The Social Function of Intellect. But a lot of these papers argue that what drove human cognitive development is the pressure of being in social communities, right? So both intergroup competition and cooperation within a group drove these ratcheting cycles that pushed us to develop our cognitive abilities farther and farther and farther. So essentially this paper is saying, could this form of multi-agent pressure induce the same kind of complexity in agent populations? And you might think, okay, this is a little far-fetched, maybe it's a little, AGI or whatever, but we've seen this, right? So this is this well-known paper from OpenAI that trained multi-agent teams to play hide and seek, and what they saw is interesting behaviors emerge even that they didn't expect. So in the bottom figures, you're seeing the agents have learned to surf on boxes, which is a consequence of the physics engine that the engineers who built it didn't even realize the agents could do. So if you're getting abilities that you didn't anticipate and didn't have to build in, perhaps that's quite exciting. Another great example, which I'm sure this community is familiar with, is asymmetric self-play. So here we have two agents competing, where Alice is trying to execute the shortest possible trajectory that Bob can't imitate or reverse. And so what that does is it makes a nice curriculum, because Alice is always trying to keep the trajectory simple if possible, but still out of Bob's range. The cool part about this is it was extended very successfully into the robotics world. So this is this asymmetric self-play for automatic goal discovery and robotic manipulation. So both of these are pretty exciting, and I'm really excited about the idea of competing agents to be able to discover and set goals for each other. I think it's also quite exciting to think about how multi-agent can aid in generalization and transfer. So obviously you guys are the real robotics expert, and I don't do that much with robots, but you're probably familiar with this example of the OpenAI hand solving the Rubik's Cube. And you'll probably know that the way they did this was they say, look, sim to real transfer is hard. We don't know exactly what the parameters of the real world are. So let's just make a simulator and randomize the parameters and create such a wide randomized distribution that we'll be able to train on the real world parameters that we'll eventually have to transfer to. And obviously this worked pretty well, but I'm going to show you that even in simple cases, this domain randomization approach can break down. So what you're seeing here is this agent is trying to walk to this green goal across a bunch of blocks. And we're using domain randomization to create a series of training environments where we randomize the position of the start state, the goal state, and the blocks. And what we can see is that when we transfer an agent trained with this procedure to this simple 4 rooms environment, we actually discovered that it hasn't learned a key skill, which is just walking around walls. Can't deal with walls, which is interesting because of course walls are very salient to us, and they could be sampled randomly. They're within the distribution of things that could be sampled with domain randomization, but evidently they're not sampled enough for the agent to learn this behavior. So it wasted a ton of time training on very similar environments to the thing you see on the left, and then isn't able to handle this use case that we care about on the right. And look, maybe you don't believe me. You guys are roboticists. Domain randomization is really powerful. Maybe you say, look, if I want to train a robot to walk upstairs, and I take my simulator and I randomize the height of the stairs, the width of the stairs, the texture, everything, and I train in simulation, and I'm able to transfer my robot to this staircase and it walks up the stairs. And you say, great, okay, I'm ready to train a household robot that can walk up the stairs in everybody's house. Well, guess what? The real world has a lot of weird staircases, right? And so could we really have anticipated that we would need to build some of these stairs into our simulator? I would argue that if like what we actually need is we want these complex training environments that can prepare us for the real world. And we want to cover these unknown challenges, but we don't want to have to anticipate them. Basically, we don't want to have to program in all the things we might encounter in the real world into the simulator ourselves by hand. Because that's just going to be really brittle. We're going to miss things. It's going to be time consuming. I don't think this is the right approach. So let's maybe take some inspiration about what other things have been going on in the multi-agent community. So this is this paper, Adversarial Policies, you've probably seen, where they were able to show that an agent trained with self-play is actually pretty brittle. So if you train an adversary to exploit that agent to just minimize its performance, it can do weird things by just falling on the ground. And this just totally breaks the policy. And if you continue to train with this in a feedback loop, you could potentially make that player agent more robust, right? So this is again tackling this idea of generalization. So what if we take this into the environment generation context? So keeping with the analogy of domain randomization, which was randomly setting environment parameters, what if we adversarially build environments or set those parameters to minimize the performance of a player agent? All right, so what can anyone see a drawback with this, a potential drawback? So here we have an adversary trying to minimize the agent's performance.
Is that for me?
Oh, is it? Do you have an answer? I thought you were putting your hand up.
Yeah, impossible to solve environment.
Impossible to solve environments, exactly. So you can see that happening in this video, right? So the adversary has built an environment where the player just can't reach the goal. So it's succeeded in its task, it's minimized the performance of the player, but the player has no learning opportunity. So again, we're just wasting computation. So what's been done in the literature to handle this problem? Let me talk for a second about RARL, or Robust Adversarial RL. So what they're doing here is they're having an adversary apply forces to different Mujoko agents that are trying to learn how to move. And these destabilizing forces, by the agent having to adjust to them, it makes the agent more robust. But the way that RARL handled this problem of the adversary, I mean, if the adversary applies too much force, it can just make the task impossible, right? And so the way RARL handled this is coming up with hand-tuned constraints that limit the amount of force the adversary could apply. And those have to be specific to each environment. So you're kind of in this realm of doing a lot of hand tuning again, which maybe we want to get away from. Another paper that I really love is called Poet. You might have seen it. And what they're doing is they're having a population of agent and adversary pairs, and the adversary is building the environment for the agent to try to learn in. And what they do is they periodically replace underperforming agents with the agent from another environment, and they're constantly evolving the agents and environments together, and they end up with this really nice emergent complexity of quite interesting environments and agents that have some impressive skills. I will point out that this paper doesn't focus on testing generalization, although I think that's something they could do with their algorithm, but they focus on this idea of like automatic curriculum through multi-agent and emergent complexity. But they still run into this issue of the adversary being able to create environments that are impossible or it's just too hard. And so what they did in this original paper is they manually test every agent in every environment, and they discard environments that are too hard or too easy, again, using thresholds that they have to tune. So maybe what we want is kind of a more elegant way to ensure the adversary doesn't create impossible environments. And ideally, we want environments that are tailored to the current skill level of the agent. So we want an automatic curriculum that increases in complexity with the skill of the agent. Okay, so I've been saying the way to solve all of our problems is with multi-agent. So maybe the idea is we just didn't have enough agents yet. Let's just add more agents, and that's going to solve the problem. So that's actually the idea behind this paired algorithm that I'm going to talk about from our own work. And here what we're doing is we're having an adversary generate an environment. And instead of having a single player agent play it, we're going to constrain the adversary using the performance of a second agent in the same environment. So we're going to take our player and rename it a protagonist, introduce the second agent an antagonist, and we're going to have the adversary build environments that maximize the difference in performance between them, or this regret. So the now the adversary is incentivized to create environments where they're possible, because at least the antagonist can do well, but they still minimize the protagonist performance. So they're still exploiting weaknesses in the protagonist. So we call this protagonist-antagonist induced regret environment design, which is a huge mouthful, but we think of it as paired because that accurately reflects how we're using this pair of agents to play every environment. So what's really cool is that Michael Dennis noticed that all of these methods I've discussed before are connected to the decision-making under uncertainty or decision-making under ignorance literature. You can think of domain randomization as actually following the principle of insufficient reason, Minimax as following the maxi-min principle, pretty obvious, and paired as Minimax regret. And the way we can show this is by introducing this new formalism, which we called unsupervised environment design. And so what we're doing is we're saying, instead of a normal POM-DP, we want to talk about an underspecified POM-DP, which has this additional set of parameters theta. So if you think of the U-POM-DP as the space of all possible grid worlds, then if you then specify a theta, which is the assignment of blocks to certain positions, then you obtain the POM-DP out of it. And when you think about how to define a policy, which defines a distribution over how to set that theta, then depending on how you define it, you can recover each of these previous works, which we think is quite neat. We were able to show in the paper that our protagonist should end up playing the Minimax regret policy, but this depends on the assumption that the adversary and the antagonist are basically acting as a team, they're coordinating. And then it becomes a two-player zero-sum game where if the game reaches a Nash equilibrium, then the protagonist is playing the Minimax regret policy. We have a proof in the paper that relaxes this assumption, so if you're interested, definitely check it out. One of the cool things about this is that we want to say that regret is going to be a good objective for robustness, because it's going to train an agent that succeeds whenever it's possible to succeed. And what we mean by that is if you can partition the distribution of rewards into two distinct modes, where success is a set of rewards that don't overlap with failure, then regret will choose the succeeding policy when it can. So this is going to be, let's get this a little more interactive. So what you're seeing in this middle matrix is a set of policies and the payoffs they get for each of these different environment parameterizations, theta. Now, if I'm doing domain randomization, I'm training an agent that just wants to maximize its average performance. So can anyone tell me what policy would a domain randomization agent pick?
I think my math is right. It would be 400 divided by 5, so any of the other rows except the first one?
Yes, you are correct. Exactly. Now, since you're on a roll, can you guess what the Minimax regret policy would be? Now, Minimax regret is minimizing the worst case difference from the optimal policy.
The policy pi a, because that gets 75 on every task or every environment.
Beautiful. Exactly. Very nice. So domain randomization is going to maximize average case performance, so it's going to fail sometimes, and that makes it not robust. Whereas regret is going to choose policy A. It's going to succeed whenever it can. So we'll see a similar example here. If we use Minimax, which is minimizing the worst case performance, that Minimax policy is going to be really afraid of the policy B because it doesn't like the -1. So it's going to choose policy A. Whereas regret, again, is going to choose policy B. So you can see that regret is going to choose successful policies where it's possible. So we think it's a good objective for robustness. I also think it's a good objective for curriculum design. So what I'm going to argue to you is that regret is going to incentivize the adversary to create the easiest possible environment that the protagonist cannot yet solve. So to make that case, assume that the protagonist is getting 0 because the adversary has succeeded in minimizing its performance. So then which environment should the adversary pick? Now, in many RL environments, including the one we talk about here, there's often a reward for finishing the task faster or in fewer steps. So if you want to just maximize the antagonist reward while keeping the protagonist reward 0, then you should pick an environment that can be solved in very few steps, aka an easy environment, right? So to think about this, you can say your regret for failing at a task is going to be higher if the task is really easy. It's very intuitive, right? So this is making the adversary continue to pose tasks that, yes, the protagonist is failing, but they're the easiest possible task that it's still failing on. So you can think of this as proposing tasks in the protagonist's zone of proximal development, which is a task that it can't do yet, but it can with some scaffolding or training on that task. All right, I want to be super clear about what we actually did for the paired algorithm, because the implementation would make a slight modification to the theory. So we randomly initialize all the agents, and then until convergence, we have the adversary generate some environment parameters theta. We have the protagonist select several trajectories in that same theta, as well as the antagonist. And using those multiple trajectories, we can get this better estimate of the regret where we take the max over the antagonist performance. So that gets it a little closer to the optimal policy, which is the true regret. And then we subtract the mean of the protagonist performance. So we think this is just a bit better. It's more of a stable estimate of the regret that tends to stay positive and not jump around as much, which makes it easier for the adversary to maximize the regret. And then what you can do with the antagonist and the protagonist is just train them as normal. They're just RL agents, they're maximizing their environment reward. So that's the algorithm. I want to jump into showing you some results, but are there any questions before I show the results?
Yeah, we have one question here from London.
Thanks. I'm just curious if you ever observed the protagonist and the antagonist learning basically the same thing. Like, how do you avoid them, if they're trained as RL agents, like collapsing to the same capabilities?
We actually see that the protagonist tends to be more robust because the training algorithm is basically going to, the adversary is constantly going to be seeking environments where the antagonist does well, but the protagonist does poorly, right? So if they're performing about the same, the adversary should seek out a new environment. So the whole algorithm is only going to robustify, if you will, the protagonist, not guaranteed to make the antagonist more robust. Now we have explored population-based approaches to estimating the regret, where you can take the max of a population minus the mean of a population. And that I'm going to talk about in a little bit.
Marco, do you have any questions from your side?
I can also keep going to the beautiful plot.
Yeah, back to you, Natasha.
Okay, so these are the environments that were actually generated from the different techniques that we talked about. So in the case of domain randomization, we see that it generates unstructured environments that aren't tailored to the agent skill level. Minimax can tailor to the agent skill level, but it can trivially create impossible environments. And paired is our Goldilocks method. It can create structured environments that are challenging, but they're still possible to complete. So if we look at the results of the generated environments throughout training, that's on the left, we can measure different characteristics. I think most interesting is the passable path length there in figure C. So this is the shortest path between the start state and the goal, and it becomes 0 if it's an impossible environment. So what you see here is that paired continues to improve this metric. The environments are becoming more complicated, but the minimax population-based training is driving it to 0. Now, if we look in figure D at what the agents actually learned, we see that the paired agents are solving more complex environments, whereas the other methods are not. And what's cool about this is nowhere was an agent trained to maximize path length, right? This is an emergent property of the system. It's kind of neat. But I think the really interesting part is what happens when we try to transfer this to a set of test environments that are increasingly challenging. So if we look at paired compared to the baselines, when the environments look more like a domain randomized environment, like the empty or the 50 blocks, the performance is pretty similar. But as the environments get more complex, only paired is able to have any hope of solving them. And so we think this is quite promising that paired could potentially increase generalization performance. So now this is all about grid worlds. I'm sure as roboticists, you're like, this is so toy, what's going on here? So I'm not promising this next is too much less toy, but I think it's interesting. When I was working at Google, there was some talk that my work should have some type of, real world product impact. And I was like, well, how are these grid worlds ever going to do that? But luckily, Sandra actually realized that paired could potentially be useful for this idea of training agents to navigate web pages. So what Google would like is you could say something like, okay, Google, go buy me a keyboard, or okay, Google, book me a flight to Los Angeles leaving on Friday. And the agent will be able to traverse these websites and put in your information and do that transaction on your behalf. But that's actually a really hard reinforcement learning problem. There's a huge action space. It's very complicated, and the websites are constantly changing. So we'll talk more about that in a second. The way the team had originally approached this was hand programming a curriculum of easy, medium, hard, and harder websites. And what you see is not only do they have to do a lot of work to do that, but the agents aren't actually succeeding on the hardest websites. And so we thought maybe paired could be used to automatically generate this curriculum. But I think the benefit goes a bit beyond that, right? Because if you're hand programming this curriculum based on the current Delta website to book flights, and we know that your algorithm is not going to generalize very well because RL algorithms have problems with that, what happens if Delta updates your website? Like, does your whole thing go down until you can retrain? How do we solve that? So maybe if you have this robustness objective, you could actually get better generalization to changes or different websites, because the internet is just so diverse. So we parameterized a paired adversary that could construct websites out of a set of components. And we saw that during training, it does generate this interesting curriculum where early in training, it generates websites with many pages, but each page has fewer components. That makes it an easier decision problem for the agent on each page. Later in training, it shoves all the components onto one page and the agent has to solve a more complicated task. And at test time, we test the agents on a set of standardized web navigation environments. And we found pretty good results. So this is actually a population-based version of paired. And we also introduced an explicit difficulty incentive based on the number of components it added to the website. And we see that that method is actually 4 times more successful than the prior state of the art in both web navigation and environment generation. And it actually reaches more than 95% task success across the difficulty levels in this benchmark. We went a step further and we applied this to real websites that we want to use with this product team. Obviously, the performance does go down from the simulated benchmark, but we are seeing some promising results there, and we're going to continue to pursue them. All right, so in conclusion, I think of unsupervised environment design as a good way to think about improving transfer and generalization for RL agents. I think paired is an interesting way to do UED because you can use this second agent as a flexible measure of the kind of performance that could be reasonably expected from your agent as you're training. And that helps you make this curriculum of feasible yet challenging environments. We think regret is a good objective for making agents robust and for creating this curriculum. All right, so I do want to briefly touch on this other thing, but I want to take questions.
Okay, so we have one question from London.
Hey, thank you so much for this talk. Jeff Clune on Monday kind of mentioned that working towards environments are like one of the 3 pillars towards like AGI, so I'm glad that someone's working on this. I was wondering what you thought about, you kind of mentioned using like, having like a population of agents kind of like navigating these like environments as they evolve. Have you considered like auxiliary tasks, for example, to kind of help with generalization, for example, instead of having the population just kind of work towards the main objective, but by having these auxiliary tasks, you could get better generalization on the main task, for example.
Yeah, that sounds really interesting. Were you thinking of a particular type of auxiliary task? Or he already sent back down?
Not in particular, but just from the papers that I remember that do auxiliary tasks, this could help, like with the example that you gave with the websites kind of always changing. If the agents are solving auxiliary tasks, like for example, being able to navigate to a button as the button changes around. I'm just kind of throwing these out there, but like as the button changes around in like the XY coordinate space of the web page, having these like smaller auxiliary tasks for the population of agents to learn would maybe then better generalize to like, you know, these dynamic websites.
That makes sense. Yeah, that makes sense. I will say, and I actually am working on a follow-up to this that is in the language space, and we are thinking about auxiliary tasks in that space. So definitely a cool idea, and maybe it makes your population more diverse, and there's interesting benefits there. I will say one thing we hope to get out of paired is that, let's say in order to learn to navigate a complicated website, you must first navigate to the button. We would expect, and we actually do see, that the adversary would increasingly decrease the complexity of the task until it does the minimum task that some agent starts solving. And so maybe the adversary would automatically learn to start with like moving the button around. That would be the dream, right? So.
Marco, do you have any quick questions? One quick question from the virtual side?
No question yet.
Okay, I think we better hand back to Natasha for the final part of the tutorial.
I only have a couple more minutes, so there'll still be time. But I just want to briefly touch on this idea of using this type of social learning in human AI interaction, which really fascinates me. So I think it's easy to make the case that you want to learn from human signals. So this is a real conversation of someone talking to their, I can't Alexa because my thing was talking to me, but they're talking to their device and they say, what's the right way to Walmart? And it responds, the right way to spell Walmart is W-A-L blah, blah, blah. So this is obviously the wrong answer. I would bet you anything that the user's response contains some hint that they're frustrated, like whether it's their tone of voice, the words they chose, or their facial expression. There's some cue there that we could potentially learn from. And I think learning from this type of implicit cue is going to work better than relying on people to manually train their algorithms. So I don't know how many people has ever bothered to train a Google algorithm by giving it feedback about whether it provided the right result, but typically people don't tend to do this. But I wonder how many of you might have used a frustrated tone with one of your devices, right? So this type of social feedback is rich, ubiquitous, natural, you're getting it for free. Why not try to learn from it? So that's something I've explored in a few different papers. This is a paper on using offline RL to improve dialogue systems, where what we did was we built a web interface where we deployed a bunch of pre-trained dialogue models to talk to people. And we tried to collect implicit signals like their sentiment. So when the conversation was going badly, you can see the user says, that didn't make sense. We can detect that that's a negative signal and train the model to try to reduce that type of feedback. Similarly, when the conversation is going well, that can be a positive signal. So this was pretty interesting. We've done some follow-ups and we were able to learn offline with the scale control method to be able to increase eliciting positive sentiment from humans. Another paper that's kind of fun was improving the output of SketchRNN by showing people samples from the model and recording their facial expression response. So actually with only 67 or 69 examples of doing this procedure, we can see that the model significantly improves the way it draws cats in the top right there and rhinoceroses. So the rhinoceroses were pretty abstract, but after only a very small amount of feedback from humans, you can improve their ability to draw credible rhinoceroses. So I think this is an exciting direction and I'd like to explore that more as future work. So I'll end there and I'll just re-emphasize why I think social learning or multi-agent systems, multi-agent approaches could be really beneficial. I think it helps you learn and complex behavior, generalize better, coordinate, and ultimately interact with humans. All right, so I promise I'm done showing slides now, so please ask me any questions.
Wonderful. Thanks so much, Natasha. And thanks for bringing the audience in with those interesting questions. That was fun. So we have a question here, Jackie.
I have two questions, but since we're short on time, maybe I'll limit it. So in the going back to the first part with the results about independent PPO, which is super interesting. Do you think so? Like the Google football environment, I'm not that familiar with it, but it doesn't seem like it's like a mixed motive game, like the tragedy of the commons environment, where seemingly the motives of the RL agents kind of conflict, like they're self-interested, but if they coordinate, then they get higher reward eventually. So do you think that result would still hold in a tragedy of the commons?
I actually have tried independent PPO in a number of different environments and I'm pretty bought in. It tends to work really, really well. I would point out the soccer environment is interesting. Where am I trying to go? So this paper, what they actually showed is that what happens in soccer is the agents don't discover diverse enough policies to do interesting strategies. So what they did is explicitly incentivize each agent to learn a different policy than the other agent with a divergence objective. So this is the celebrating diversity paper. they get really good results. But I think independent PPO, because it's fully decentralized, also enables this. Agents can learn independent policies, so in that sense, be diverse. But what's interesting is I think the diversity objective at some point may work against the game objective. Like once you've got this diverse mode, maybe you then want to optimize, whereas PPO is free to fully optimize the game reward once it's discovered different policies. So that's kind of why potentially it could be quite good in this environment, but I actually think independent PPO is quite solid. The other thing, I don't know if you saw this paper from a few years ago, which was showing that PPO is just much more stable and easy to train than other algorithms, like even than SAC. So it just works across a broader set of hyperparameter settings and tends to be really reliable. So that might be why it's still a good choice if you're just getting started in multi-agent, because it's easy to get working.
Thank you. Marco, do you have any questions on your side? Just
Yes,
time for one.
Yes, there is a question. So for the rhinoceros case, how did you measure if the face expression is a positive or negative signal for the drawing agent?
That's a great question. Actually, we used we distilled their facial expressions into things like smiling and frowning and stuff like that, and we assumed that we want to maximize smiling and I don't know, smirking or something, I forget what exactly where, and minimize frowning and concentration. So it turns out concentration often looks like the person is just unimpressed with this thing. The way we actually established this, though, I should say, is we did extensive UX studies. So we actually worked with the whole UX team. We did user studies in the beginning to have people interact with SketchRNN, looked at what the detector was detecting and correlated that with their ratings of the sketches. So we didn't just make this up. We actually did the groundwork to establish what is the relationship between people's actual perception and their face. So.
Great, thank you.
All right, and we'll finish with one final question from London.
Thanks a lot for this really interesting talk. So with paired, one of the things that just thinking about how we take it further and be able to use it in robotics, I guess, is how would you be able to scale up kind of the way the environmental encoding is? So with your maze, I guess, sort of automatically generating it, but as we want to move into perhaps more complex and more realistic 3D environments, how do you think you'd be able to encode the environment that kind of lets paired use and explore the environment in a way that we kind of can see and as meaningful as we train the agent?
That's a great question. And I think there's a lot of complexity there. You might be just passing the buck of all the hand coding I was complaining about into the parameterizing of the adversary. But I actually think anytime you could be applying domain randomization, you've already got a set of environment parameters that you're randomizing where you could apply paired, right? The other thing, and you could tell me if this is a crazy or a bad idea that I was thinking about, is what if you could parameterize, if you're interested in like object manipulation, what if you could parameterize an environment so that you could build new objects? And then you can get a manipulation policy that's robust to many types of objects. So like maybe you can stick different components of objects together and get something new for the agent to manipulate. But I don't know if that's a bad idea.
No, I don't know a lot about sort of the object manipulation side of things, but I think it makes a lot of sense to have your environment be parameterized in something that maybe the designer already knows is a useful thing to get behaviors out of, right? Because it's maybe a way to put information we already know about how we want the behaviors to behave beforehand, perhaps.
Yeah, that makes sense. That's a great point.
Cool, thanks a lot.
All right, so it's 5 o'clock here in London, so we'll have to end there. And Natasha, thanks so much for joining us and for your wonderful tutorial.
Thank you.
Thank you very much.